Hi, here's something you don't see every day. What this is an original DC Johnson FAC-3 emission control device kit. This thing was manufactured 30 years ago, and it's the only remaining production unit that's still in its original packing. Let's open up the kit and see what's in it. This is FAC-3, and it was originally designed to convert the 1984 and 1985 Porsche 928 with the LH Jetronic fuel injection system. This is the original warranty card. It's useless. The thing has been sitting in storage for 30 years, so even though it's still intact, there's no way that this thing can be covered by a warranty. Here's the unit, and here's the remainder of the kit underneath this cardboard divider. Here's what 30 years will do when there's a little bit of acid in the paper. There's the installation wiring diagram. And here's the remainder of the kit. A shielded cable for the oxygen sensor. This shielded cable gets extended with a piece of Teflon insulated wire for high temperature resistance. And this is the main wiring harness, 6 wires. This connects to the FAC unit here, and then these 6 wires connect into the original wiring harness of the fuel injection controller or brain. Two inline intercept splice connectors and 4 butt splice connectors. Those are all of the connectors needed to install the main harness. Okay, so what I'm going to do here is prepare this unit 30 years after it was manufactured. Let's open it up. Here it is. As you can see now, I've set up my bench to test this FAC-3. To do a thorough test on it, you need a couple of voltage sources. So I have a couple of bench power supplies here and some meters. You could use 1 meter if you want, but I have several, so I'll just use several individual meters. Before we start with the functional test, I want to go over how this thing operates. This FAC-3 is a variant of the FAC-2. The FAC-2 controls the air-fuel mixture on vehicles that are electronically fuel injected that were manufactured before they had onboard diagnostics or more sophisticated digital controls. And more importantly, fuel injected vehicles that were not originally manufactured with an air-fuel ratio closed loop control using an oxygen sensor. The oxygen sensor circuit is what this adds. The FAC-2 had 2 trim potentiometers. This one here is for adjusting the oxygen sensor input signal offset. This one here is for adjusting the cold starting switchover threshold, where it runs in open loop for a period of time with a rich mixture until the engine temperature has warmed up sufficiently. This is an FAC-3, which is a variant of the FAC-2, and it adds this 3rd trim potentiometer, which gives the installer the ability to add another level of trim control on the mass airflow meter signal coming from the hot wire mass airflow meter. Whether it's an FAC-2 or FAC-3, it will have a capacitor here which provides the delay before switching from open loop to closed loop under hot starting conditions. The FAC-3 had a much larger capacitor than the FAC-2 here. It also adds an additional capacitor on the back side here. These are both there to increase the hot starting delay in order for the vehicle to run in open loop long enough for the oxygen sensor to reach full operating temperature. As you can see here, I've already updated the oxygen sensor cable to a Teflon insulated cable. So now I'm going to hook the thing up and see how it works. Okay, one of the first things we need to check when we first power it up is the power supply voltage. So let's have a look. Okay, there's our battery voltage. And here's our output voltage on the voltage regulator. The next thing we need to check is the oxygen sensor offset voltage. Now, this thing's been sitting around for 30 years, so I'm going to sweep the potentiometer through its range a couple times just to make sure the wiper's clean. That's about as close as we're going to get it. Next, we want to check the cold start set point threshold, and that's the wiper of this potentiometer here. Looks like it's exactly where it needs to be. Now that we've verified that it's powered properly and the settings are correct, we are going to give it a functional test, and for that we'll focus on the meters showing the appropriate voltages. The red meter on the left shows the simulated coolant temperature sensor input to the control unit. I can adjust that voltage here. The yellow meter in the center shows the simulated oxygen sensor signal, and I adjust that one here. The black meter on the right shows the output of the fuel air control unit. Okay, so now what we're going to do is simulate a hot start. The coolant temperature sensor voltage is low, indicating a warm engine. The oxygen sensor voltage is low, indicating cold or lean mixture. And this again is the output of the device. It's floating right now because the device is switched off. So let's turn it on and see what happens. So we get an elevated voltage on the output for a short period of time, and then when we adjust the oxygen sensor signal, as you can see, I've brought it up to a high level and the output voltage goes down. Let's do that one more time. Okay, the unit is switched off once again. We have a low coolant temp sensor voltage indicating a high temperature. This time we'll have a high oxygen sensor voltage indicating a rich condition, and we have the output voltage floating, tracking the input voltage. So what we should see when we hot start it is we should see an initial delay in the change of the output voltage. The output voltage will remain at a high level for a short period of time, and then when the circuit switches from open loop to closed loop, the voltage drops to near zero. The low oxygen sensor voltage, the output raises up and will continue to gradually climb. As I oscillate the oxygen sensor voltage from low to high, the output voltage corresponds in the opposite direction. Now we will simulate the condition of a cold start. In a cold start condition, the coolant temperature sensor is cold. The oxygen sensor is initially low because it's cold. The output voltage of the unit tracks the coolant temp sensor voltage directly when the unit is switched off. There is a bit of a voltage drop there, not much. So let's turn it on and see what happens. Okay, as you can see, once the unit is powered, the voltage drop has gone away, but nothing else is happening. Now, as the engine warms up, the oxygen sensor voltage will increase. Still, we have no change on the output. At some later point in time, the engine starts to warm up and the coolant temperature sensor starts to reduce in voltage as the heat increases. Once the voltage of the coolant temperature sensor reaches a threshold to switch, the system switches from open loop to closed loop. At some point, and as you can see now, the oxygen sensor voltage is controlling the output. Lower oxygen sensor voltage, higher output. Higher oxygen sensor voltage, lower output. And that's how the system works.